Hi, my name is Scott Briggs, and I'm the president of the Michigan Mars Rover team, or Rover. We're a student-run, multidisciplinary project team here at the University of Michigan, whose goal is to design, build, and test a rover for the exploration of extraterrestrial environments and to assist astronauts on a mission to Mars. In this presentation, we will go over the team introduction, including the team structure, organization, and management, the design and functionality of the core rover system, and the suitability of the rover design to each of the 4 competition tasks: terrain traversing, astronaut assistance, equipment servicing, and the science cache task. Our team members gain experience with the real-world design process, which supplements theory learned in the classroom with hands-on knowledge. By working together to address the tasks of the University Rover Challenge, our team members continue to develop interpersonal skills as well as broaden their understanding of different fields. Rover is made up of 24 active members from a variety of academic backgrounds, both in engineering and otherwise. Our members consist of everyone from freshmen to graduate students pursuing degrees in areas like mechanical, electrical, and aerospace engineering, computer science, and geology. The wide range of member experiences and class standings promotes innovative ideas and enhances the team dynamic, while also enabling the team to build its organizational knowledge that will be passed along to future classes of Michigan engineering students.
Rover is organized into 2 main teams, mechanical and electrical, each with their own sub-teams. The mechanical team consists of chassis and suspension, steering and drive, robotic arm, and soil sample collection sub-teams. The electrical team consists of wiring, onboard, and base station sub-teams. These explicit divisions of the core rover system help ensure that all potential action items are covered and help create an environment of responsibility and accountability within the team. Within each sub-team, members are assigned tasks that push them beyond their current knowledge and experience, and often require them to interface with members of different disciplines. Rover's team management consists of a 5-person executive board that facilitates the functioning of the organization and the rover design from a systems level, serving as a solid foundation that the team is able to build and grow off of. These positions include the president, who's responsible for the vision and long-term goals of the team, the vice president, who focuses on short-term goals, the chief engineer, who's responsible for technical collaboration as well as the work breakdown, the treasurer, who leads the fundraising effort as well as organizes the team budget, and the information systems officer, who is in charge of the website, electronic records, and other social media accounts. While each executive board member has responsibilities from a leadership perspective, they are also members of individual sub-teams and are heavily involved in the designing, building, and testing efforts as well.
The Rover core consists of a 6-wheeled, remotely operated mobile platform that is controlled by an operator at a dedicated base station. The operator uses a joystick to drive the rover, control the robotic arm, and actuate other devices on the rover system. Data from sensors, cameras, and other onboard instrumentation is collected in the onboard computer and wirelessly relayed back to the base station computer. The base station software then communicates this information to the operator through a custom user interface, which closes the feedback loop.
The chassis of the rover features a bonded carbon fiber tube design with rivets to ensure proper alignment during bonding. This method takes advantage of the favorable strength to mass and rigidity to mass properties of carbon fiber. Structural interfaces were a key point of improvement with this design. A destructive drop test of Rover with a similar chassis design showed that fracture of the tubes initiated at load-bearing holes drilled in the carbon fiber, which makes sense due to the stress concentrations in these areas. This result led to the use of bonded aluminum U-shaped connectors at the structural interfaces with the suspension and arm to eliminate the geometry effect of holes in the chassis tube and improve the loading discontinuity at these locations. The Rover suspension system makes use of a rocker bogie design with differential bar, the favorite design for NASA's Mars rovers, to passively ensure contact between each of the 6 wheels and the ground, as well as a neutral chassis angle. Made primarily of square aluminum tubing, the suspension joints are welded together, allowing for a simpler design and reduced fabrication times. The 2 sides of the suspension are fastened to the chassis through the U-connectors and are connected to each other through a differential bar that pivots on top of the chassis frame. One notable addition to the system is a mechanical hard stop above the bogie to prevent bogie inversion, an issue identified in previous testing as well as academic literature.
To drive the rover, 6 independently powered in-hub motors are mounted to the suspension, and each motor connects to a wheel through a custom manufactured aluminum hub. The wheels themselves consist of a 10-inch diameter, high-density polyethylene tube, foam and rubber layers, and silicone molded rubber treads. To maneuver the rover, skid steering is used for its simplicity and lighter weight. The rover's robotic arm has 6 degrees of freedom and is mounted to the front of the chassis via 3 U-connectors. These connection points make the arm completely removable for easy maintenance. The 4 main components of the arm are the base, elbow, wrist, and the end effectors. The base contains 2 transmission systems. A base rotation motor drives the chain and sprocket to control the yaw of the base, while a shoulder lift motor controls the pitch of the upper arm. The elbow joint, which is connected to the base through epoxy carbon fiber tubing, utilizes a parallelogram linkage that allows its motor to be mounted closer to the base, reducing the load on the shoulder lift motor. A water-jetted forearm connects the elbow to the wrist. The wrist has two motor transmission systems which allow it to achieve a range of approximately 270 degrees of pitch and 360 degrees of roll. It also has a modular design that lets us switch between our hand and auger system end effectors depending on the task. The robotic hand uses a worm and gear transmission to drive a parallelogram 4-bar linkage system that opens and closes the hand. While the body and the links of the hand are made of water-jetted aluminum plating, the grippers are 3D printed nylon and have a foam and rubber layer to conform around objects for increased contact.
The electrical team enables the operator to control and receive data from the rover. It is comprised of the onboard hardware, onboard software, and base station software. For the onboard hardware, the electrical box and auxiliary components have several key features that set this year's design apart.
An astronaut on the surface of Mars would need to be able to quickly and easily remove the electrical box from a rover to diagnose problems and find solutions. To achieve this, we designed a box that is fully modular and is able to be removed from the rover chassis without the use of any tools. We used weatherproof connectors and filtered fans to protect the box from a harsh desert environment.
The communications protocol was designed with three main goals in mind: to be lightweight, reliable, and redundant. To be lightweight, we used UDP, which will allow us to avoid the packet renegotiation and session control features of TCP. To be reliable, we implemented UDP acknowledgements, which is a simple message to the rover or the base station indicating that the other has undertaken a particular action. The combination of these two features allows us to be redundant, giving us the ability to drop any number of packets and still retain control over the rover.
In order to make the rover control more accessible and intuitive, we developed a user interface. The user interface displays sensor and status information received from the rover. In the interface, there are sections devoted to feedback from the drive and arm motor systems, environmental sensor data, diagnostic information, and a map of the competition location. The map uses GPS coordinates to visually display the rover's current location and its destination. The custom interface provides feedback more clearly than a command line interface and allows the operator to make more informed decisions.
The terrain traversal task was a key design driver for the chassis, suspension, and drive system. Several key advantages in our design enable the rover to traverse a variety of terrain. For rough terrain, the rocker bogie suspension allows for easier traversal of uneven ground due to the large suspension travel, as well as a more neutral chassis angle. A chassis ground clearance of 14 inches, along with in-hub motors, ensures that the rover can pass over larger obstacles, like rocks and small ridges, and irregular terrain without damaging key components. Due to the presence of hills in the competition area, our motors were selected with high enough torque to allow the rover to traverse inclines in excess of 60 degrees. In practice, however, the ability to drive up steep slopes is likely traction limited. To counter this, treads on the wheels were custom manufactured from a polyurethane rubber using silicone molds. Testing has shown that these treads have led to improved traction on loose rocks, gravel, and sand, which we expect to be consistent with the ground conditions at the competition site.
To improve the ability to navigate to a specified location and deliver tools to astronauts in the field, a GPS mapping tool in the base station GUI was created to display the desired location and the position of the rover, which is updated in real time. Once within the provided vicinity of the object, the main camera with pan and tilt servos and camera mounted on the arm's wrist can be used to more precisely locate the equipment and deliver it to the astronaut within 1 meter. With the hand's parallel grippers, objects can be uniformly grasped and then manipulated to the rover storage rack, which is mounted on top of the shelf above the electrical box, or delivered to the astronaut. In addition to the dexterous movements required in the astronaut assist task, the arm's 6 degrees of freedom allow a larger workspace to be reached with the end effector, which is useful for the unknown location of the mock service panel components. Moreover, a maximum grip width of approximately 12 centimeters for the hand makes it versatile for the many unknown valve knob and fuel can sizes. Because precision in the arm position is most important when handling the fuel and oxygen tanks, feedback from motor controllers will be used for more accurate control and manipulation.
So our team selected a auger rather than a scoop or a drill to remove the soil and retrieve the sample because of the versatility and also the fact that you can both break into the soil and also remove the sample at the same time. We also have a temperature probe and humidity probe on a linear actuator, which is attached to the chassis of the rover. And so those are driven into the ground near where the sample's being broken up to record readings at the required depth. Once the once the soil sample is actually inside the rover, it's brought into 2 containers which are sealed by a spring-loaded mechanism to prevent contamination. There are 2 containers, one which is pre-wet with deionized water. In this container we're going to be doing pH and conductivity testing. The other container will be kept dry and sealed and used for later testing at the base site. And so we selected pH testing because it's pretty ubiquitous in the soil characterization community. Life on Earth typically favors a near neutral pH of 6 to 8. And so if we do get a pH level of near that value, then we know that if there is water present, it should be favorable for life. On board, the conductivity will be done on a wet sample. And what this does is it gives you an idea of the ionic strength. And ionic strength is determined by the number and valence of the dissolved cations in the water. So this gives you a rough indication both of how soluble the constituents of the soil are and also if they're related to hydrous processes, because hydrous minerals dissolve easily and are also deposited and precipitate in wet environments. So this wet conductivity measure will give us an indication of what the environment was like and also what it currently is like.
With this core rover design and proven suitability for the 4 competition tasks, we are confident in our ability to perform well in the 2016 University Rover Challenge. And on behalf of the Michigan Mars Rover team, I'd like to thank you for watching.